Hello and welcome to a new Algebra 1 video. This is a new and short unit we're going to do talking about functions. This is lesson 1, Introduction to Functions. The word fun is there in the name, so you already know you're going to have fun. Just right off the bat, it's right there in the name. So let's talk some vocabulary. What we do kind of from algebra up is we like to think of things that have relationships with one another, numbers that have relationships with one another. And we just call it a relation most of the time. And so anything that takes two sets of numbers and links them together somehow is a relation. So it could be that we have a list of ordered pairs or a table of values. We could have a graph. We could have a line graphed on a coordinate plane. We're going to see a new thing called a mapping in the lesson today, that all these things can represent relations, and it's just a way to say, hey, you have this number and it goes to this other number. You have an input that you're putting into something and you get something out, that kind of thing. A function is a specific kind of relation that we care a lot about in math. It's a relation where each input has exactly one unique output. And if you think about it, that's the thing that makes sense, right? When you do something happens, cause and effect, that's kind of the thing. And so we like functions for that reason, that they're predictable and things like that. And so what we're going to start off with here is seeing what functions look like and how to tell when something is or isn't a function. We have another name for the set of inputs and outputs. We call the set of inputs domain and the set of outputs range. So in our definition of relation, I said there's a lot of ways that we can represent a relation. Here are examples of those four things I listed. These are not examples of the same thing. Like, these are all four separate situations. It might have made more sense for me to just use the same numbers 4 different times, but I didn't do that. So I'm trying to get the point across to you that these are not the same. These are not representing the same situations, okay? So look at them kind of separately. Ordered pairs, that's something that we have dealt with before when we were graphing, right? You can graph points, but you don't actually even have, that's not the only thing you could do with points. You could make a list of points to show what numbers go with which. So the x value is our input, the y value is our output. And so ordered pairs are saying whenever I have 2, like in this first point, when I have 2, I get 3 as an answer. When I have 4, I get 5 as an answer. Now that's a little weird whenever you don't know what it is that makes the connection there. But all we technically need is a list of results, kind of. Same with a table of values. So this would be like an x column and a y column. And again, it's just relating these two things together, 1 and 3, 5 and -2, 0 and 8. A graph is a way we can relate x and y values or inputs and outputs, because each of the points on this line have an x and a y. So the line itself is kind of connecting them into a relation that's happening. And what's great about things like a graph with a line is that they have a predictable pattern. Whereas these ordered pairs table and even the mapping I just made up, like if we wanted points on this graph, they would legitimately have to be points on this line, right? Like 0, 3 would be a point that would be on that line. And then the other points follow a pattern, an equation. So that's neat. Anyway, last one of these, mapping. This one is weird and also may not seem like super similar to these other ones. It's definitely not something we usually do outside of talking about functions in algebra, but we can actually do a visual representation by making a list of our inputs in one column, and we usually put it in a circle, or I made like an oblong rectangle or whatever you call it. And then, so we do a list of inputs, and then we do the list of outputs, and then we draw arrows across to show the relationship. And so we're going to draw one of these later on, so you'll see, but this actually all of a sudden made me think of Among Us, and it made me think of when you do wires in Among Us. Hopefully Among Us will stand the test of time, so this analogy is something I'll be able to use for years and years to come. But think about whenever you do wires on Among Us, and that's kind of what a mapping is. So this first example, I want us to just get used to the idea of the fact that we can represent the same data different ways. That's not what was happening on the slide before. Those were all different situations. But here I have a list of ordered pairs, and I can reorganize that information into a table, a graph, or a mapping diagram. So for our table, we could put X and Y, or we could put input and output. And what we're doing is we're going to put our X values in one column, in the left column, our outputs, which are the Y values, in the right column, and we just put them next to each other so that we know that it's talking about a certain point. So like we put -1 and 2, and then we move to the next one. And then anybody looking at this knows -1, 2 is a point for this relation. So we just do that with each of these. 3, 1, 2, 3, 0, 4, and -5, -3. Okay, easy peasy. Just taking the ordered pairs and saying, here's what it would look like as a table instead. What would it look like as a graph? Now these are 5 separate points. And even though we as human beings, I think, are conditioned to connect dots, there's nothing in the problem that tells us to connect the dots, because it's saying -1, 2 is part of our graph. So it's saying 3, 1 is part. So here, that's part of our graph. It's saying 2, 3. It says 0, 4, and it says -5, -3. So nowhere in there did it tell us if we should connect the dots, how we should connect the dots. You might be going, whoa, you just connect them in the order that they're listed, right? Well, no, there's nothing mathematically telling us to connect these dots. I guess you'll just have to trust me on this. I don't know. So let's do a mapping diagram. Now, I have a pretty large appreciation for mapping diagrams that has developed over time, because I just think that this is like one of the cooler ways to represent a relation or function, because you get to separate it into the inputs and outputs, the domain and the range, the x's and y's, however you want to say it, and then you get to just like draw arrows to show what numbers are connected. I guess so I just said it reminded me of the wires in Among Us, and that's true. And I just did a video on that. You should go check it out. But also it reminds me of back in the day matching, which maybe you get to do matching on a regular basis, but I'm an adult and that's not a thing that comes up a lot. You know, where you have, like when you were really little, you would match like capital A with lowercase a, and you draw a line between them. And I don't know why I'm telling this story, but that's what it reminds me of. And so I think there's some happiness that can happen here with mappings, even though they look kind of different. So you could just put them in the order they're in, but typically we put them like in order from least to greatest. And I especially want to do that because I want this to actually be interesting. And if I just put them in the order they are, you're just going to draw arrows across, and that's boring. And it's okay if you want to be boring, but I don't want to be boring. So here's my list of x values. So I just went through and did most negative to most positive. Now I'm going to look at the y values and do the same thing and hope that, based on the way I pick these numbers, that this works out. -3, 1, 2, 3, 4. Okay, so -5 goes with -3. This is not necessarily the way we wanted to start because that's boring. -1 goes to 2. So, yeah. 3 goes to 1. And 2 goes to 3. And 0 goes to 4. I did that in like a weird order. But there we go. We've drawn the arrows across so that we can see the relationship. Honestly, that's one of the least helpful ways for us to show it, but it's kind of cool that we have this way of showing it. I don't know. Okay, let's say that we think of functions as being a machine. When you put something into the machine, you get something out. There's some sort of rule or association that's happening inside of the machine. And so you put in the number, like on A for this first point, you put in the number -2, and then it spits out 2. So it spit out one thing. So it's not a function if when you think about a number as an x value, then you have to think of 2 answers. If none of the x values are repeated, then that means that all of our outputs have to be unique. And let's look at how that works. On A, I'm just going to look at the x values and say -2, -1, 0, 1. Those are all different. So nowhere did they tell me a second answer for -2 or a second answer for -1, because all of these are different x values. So this is a function. And since it is a function, we are going to state the domain and range. So domain and range, which we haven't really talked a ton about, is another way that we it's a fancy math word in some ways for us talking about inputs and outputs. So the domain is a list of the numbers that are our x values or our inputs in this situation. So our domain here is -2, -1, 0, and 1. It's kind of like it's splitting our points up into x's and y's. Domain is x, range is y's. It's in alphabetical order, just like x and y are, which is nice. So then our range is 2, -1, -4, and -7. You can abbreviate domain and range as D and R if you would like to. So what's the other situation? How do we know when something's not a function? Well, take a look at these x values. We've got 1, 0. Well, wait a sec. We've got 1 again. So this is saying that whenever I put 1 into the machine, I get back out 5 and -2. That doesn't even make sense, right? Like with the way we think of how things work most of the time in the world. So that it just doesn't seem like that should make sense. So this is not a function. And then since it's not a function, we're supposed to explain how we know. We know it's not a function because 1 has multiple outputs. Or something to that effect. You could maybe write it a little bit differently like that, but still get the same kind of point across. Example 3. So with the mapping, it's really similar, but there's a visual way that we can look at it that makes it really easy as well. If we're thinking of it like we do with ordered pairs, we'd say, do we have unique x values? But the way that plays out is that our x values should all have one arrow going to our y values, because that's the way that we would represent something having 2 answers. So on A here, -4 has one arrow showing where it's going. So it has one answer of 0. 0 has one answer of 2. 4 has one answer of -2. And I can tell that because they each have one arrow headed out from them. So this is a function. And the domain is just the inputs. And the range is the outputs. For B, we've got 1, 2, and 3. So we don't have a repeated number because it's just 3 different numbers. But check out the arrows from 1, coincidentally again. 1's our problem. 1 is saying that it has an answer of -3 and an answer of -1. So you put 1 into the machine, you get out 2 answers. That's not supposed to happen. This is not a function. And it's actually the exact same reason, even down to the fact that the number 1 was the issue. 1 has 2 outputs. So I think that's similar to what I said on the last one, but you can kind of change up some of the words and have it say the same thing. Saying no because it's not, that's not a math answer, a good math answer. So, table of values, think back kind of to ordered pairs. If all our x values are different, then they all must be pointing at a unique thing. If all our x values are different, then they can't have told us that a single x value has 2 answers. In order to have that happen, we'd have to have 2 places where we have the same x value showing us 2 different answers. So A actually is the one that's not going to work here because it's telling us that 1 goes to 3 and 5. That's 2 answers, so it's not a function. And ironically, again, the number 1 is the issue. 1 has 2 outputs. So it is not a function. But here on B, -2, -1, 0, 1, those are all different. I want to point out real quick, it's okay that we have a repeated output. So those are different things. You can put in a -1 and get 1 as an answer. You can plug in +1 and get 1 as an answer. And that's okay as far as it being a function because we want each x to have a unique y. But that doesn't actually mean our y's have to be different from each other. I know that's kind of weird, but trust me, we just care that the x's are not repeated here, so it's a function. And then we'll say our domain and our range. And you really shouldn't write the 1 twice because it's just a list of numbers, and that just because the 1 was listed twice doesn't mean you have to list it twice in the range. If we were doing a mapping of this, it would be cool because we'd have 2 arrows. We have 2 arrows from the left that would come in to 1. I don't know. It makes for a different mapping. This is the joys of a math teacher's life, thinking about these things. All right. You might be thinking, oh, graphs, those are going to be harder, right? This is one of the times where it's not. This is the best part of functions. In 2 years in Algebra 2, when you go over functions again, you're going to go, I don't remember any of this. And then your teacher's going to say, what about the vertical line test? And you're going to say, the vertical line test, I don't quite remember what it is, but I remember I loved it. And then the teacher's going to explain to you, the vertical line test is a way that you can tell if something's a function, because if you put a vertical line on it and it goes through the graph more than once, it's not a function. If anywhere you put a vertical line, it would go through the graph only one time, it is a function. So let's check out this circle. If I draw a vertical line, I don't even have to try very hard to find a place that this happens. If I draw a vertical line almost anywhere on this graph, it goes through the circle twice. That means it fails the vertical line test and it is not a function. Okay, so that's what it means to use the vertical line test. That's what is the case where it fails it and it's not a function. It passes the vertical line test on this next one, where anywhere you choose to put a vertical line on that graph, it only ever goes through at one spot. And so this is a visual representation of this idea that our x values are only supposed to have one y value. So on the circle, our x value of 0 has 2 places that it hits the graph. So plugging in 0 for x has to give us 2 outputs. So that doesn't mean that circles aren't a thing or that they're not valuable in their own way. It just means that we don't call them functions, and so they don't act the same as functions do. That's, by the way, why we care about functions, is because we can classify things that are functions and analyze them in similar ways, and that's something we do with functions that we can't do with all relations. So let's take a look at this example, although those kind of were a couple of examples. So on example 5 here, we're not gonna, well, I wasn't gonna worry about the domain and range, but I'll go ahead and tell you the domain and range on these, but I do want to point out that domain and range on graphs is a bit trickier. Okay, so it's fine if you want to save it for later, in my opinion. So the vertical line test here says if I draw a vertical line on any of these places where I have a graph, it should only go through once. If I draw a straight up and down line on any of these points, oh, I'm not doing a very good job, but yeah, it only goes through a single point. So a situation where it wouldn't be a function, if you have points like this, is just having one point above the other. That would fail the vertical line test. Just kind of in case you were having trouble visualizing what failing this would look like. So this is a function. And so the domain is the x values from our points on here. So -1, 2, nope, I just messed up. See, that's why, part of why I didn't want to deal with it. -1, 0, 1, and 2. But our range is the y values. So there's one at 0, then at 2, then at 3, and then at 4. So that would be our domain and range on this one. B, this is a line. And a line can be a function. In fact, most lines are, because when we draw a vertical line, it only ever goes through in one spot at a time. So this is a function. Then C is not a function. I am going to skip the domain and range because my battery's about to run out. And that's because if I draw something like right here, for instance, it goes through twice, so it fails the vertical line test. Thanks so much for watching. I hope that you liked the video. I hope you literally liked the video. Please subscribe if you haven't already. Leave me a comment, tell me how it's going, and I'll see you in the next video. Bye.